Okay, so when you take a look at this function y equals x to the x, it looks, pretty harmless in and of itself. Okay, can you see what issues might come about when trying to determine values of x to the x? Can you think of an x value that would cause issues? And it's an issue we've seen before with something that looks familiar.
Maybe like 0.
Okay, certainly 0 is definitely a big issue. Good. Yeah. Anything else? And maybe focus on the exponent there. What might cause problems in the exponent? And I'll give you a hint. We had this problem when we started considering exponential functions. Well, what if I were to take x is equal to, say, -1/2? Okay, so that means y would be equal to -1/2 to the -1/2, which, of course, is just going to be equal to 1 over the square root of -1/2. So can you see that the function won't be defined at -1/2? But then what happens if we change this to -1/3? Is there any issue here? Can you find a solution to this expression?
No, because it's still negative.
Oh, yeah, but now we're taking a cube root, and we can take cube roots of negative numbers. Okay, think of -3 times -3 times -3 is -27. So you can take the cube root of -27. All right. And so what you find is similar to what you had with exponential functions, is that when x is negative in this scenario, weird things starts to happen. Sometimes it exists, sometimes it doesn't. And I think when we take a look at a graph, we're going to see that same issue comes about. But the question I have here is, and this is what I want you to ask yourself, is why don't we have the tools to differentiate this? So who can tell me why I'm kind of stuck? Like I said, even though it looks in some ways very familiar, the fact is that we actually don't have the tools to determine the derivative. So what is the issue here? And maybe think about what we can determine the derivative of.
I'm not sure if this is like the point, but you have to like plug in a value of x, which means that it would be a constant, so it would be 0. Because if you didn't plug in a value of x, it would sometimes exist and then it would sometimes not exist, depending on if it was like the odd or even.
Yeah, and for sure that would be an issue in terms of determining y values. But remember, when we're trying to determine the derivative, first we find the derivative function, and then we would input a value. So certainly there would be an argument based on what we talked about here, an argument that we're probably not going to define this for numbers that are less than 0. Yeah, Sammy.
I think because we kind of learned how to take the derivative of like power functions like x to the a, and then like derivative functions like a to the x, but x to the x kind of fits neither of those forms.
Yeah, and that's what it comes down to here, is what we learned how to take the derivative of was a power function, which was a variable base to a fixed exponent. So that's our, n times x to the n minus 1. And we learned how to find derivatives of fixed bases to variable exponents. And the fact is that this does not meet either of these requirements. And I think when we take a look at the analytical scenario, we're going to see that we're going to end up with something in the limit definition that looks different, that doesn't offer us the options that we had when we were looking at the derivative of x to the n, where the power was fixed, and when we were looking at a to the x, where the base was fixed. Okay, so here y equals x to the n. Oh, it's not x to the n, sorry, x to the x. Okay, is neither a power function or an exponential function. Okay, so it doesn't fit either of these functions for which we found the derivative formula for. Okay, so we need to start from scratch here. So the first thing, kind of suggest that we do is we take a look at it graphically. Okay, so what I'm going to ask you to do, I'm pretty sure I can pause this. Can I pause the recording? I'm going to pause the recording and I'm going to give you a couple of minutes to put that on Desmos and see what it looks like. All right. So take a look at that. Think about what the derivative should look like without using Desmos. Okay. So, sketch what you see on Desmos for this function on this Cartesian plane, and you should be able to draw, see if you can figure out what the graph of the derivative should look like. Okay, and then check it with Desmos. So again, just a reminder that if you want to use the power of Desmos, define it in Desmos as f at x equals x to the x. Okay, I'm going to pause and give you 2 minutes to look at that. Zoom the recording. All right, so if we graph y equals x to the x on Desmos, you see here that you're not actually seeing anything on the other side. Now, I'm curious that I think it might be because I don't have, I thought I would see something to the left, but I guess Desmos is recognizing that. And we see, not surprisingly, that, things we expect to get funny on the left. Okay, so when you think about it, it's a pretty simple looking function. Is there anything you want to say about the end behavior about this function? If you had to compare this to the end behavior of other functions, any comparisons we can make about what's going on with the end behavior? Well, clearly, as x approaches positive infinity, the y values are also approaching positive infinity, but anything you see about the way they're approaching positive infinity?
They're approaching in a manner of like powers, almost as if it was like a quadratic or cubic sort of way.
Yeah, it's definitely getting big quickly. In fact, I'd almost say it seems to be going quicker than that, maybe even quicker than. What are our quickest functions so far?
Quartic.
Oh, even bigger than that.
Exponential.
Yeah, the exponential functions. Now, you might look at this here and say, well, this exponential function, 5 to the x, seems to be growing much faster. But I'm pretty sure that if I change my thing here and allow myself go to, like, let's try 1,000. Oh, maybe that's not enough. Oh, sorry, 1,000. Okay. Can you see what's happening? Do you see how this green one is, suddenly not growing quite as fast? Let's make it even bigger. Let's go to 10,000 here. You see what happens? The red function eventually takes over the x to the x, even though at the beginning seems to be growing slower. Once you get to a certain point, it starts to grow faster. Okay. And if you think about it, does it not make sense that x to the x would grow faster than an exponential function? Because it's not just the exponent that's getting bigger, it's also the actual base that's getting bigger over time. Okay, so I think I may have referenced that, we think of exponential functions as the quickest functions that we're going to be dealing with. And that is correct, because we are going to spend a lot more time working with exponential functions and not so much with this function, say x to the x, but this function actually grows faster than an exponential function. So number one. So if I'm trying to figure out what the derivative is going to look like, well, what's happening? Is there any particularly interesting point that you might point out here?
Well, I had a question before that, but the point could be maybe like 0, 1.
Yeah, so 0, 1 definitely
1,
where
1.
it's going, and it passes through 1, 1, which makes sense because if x is equal to 1, 1 to the 1 is equal to 1. Is there something interesting going on somewhere in between?
Oh, my question was, I don't know. Why does it go down? Like, it goes down and then up.
Well, remember what happens when you're taking square roots. Okay, what happens? What
gets
does a square
small.
root? Exactly.
Or,
Okay,
yeah.
so clearly, but the other thing we have to keep in mind is it's not just the exponent that's changing, it's also the base that's changing. So I guess there's almost like this competition happening between the base and the exponent. Like when they're both greater than 1, well, there's no question, it's just going to get big, 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 big. But when you're between 0 and 1, and we know that roots, try to make the number smaller, but the base is also increasing. So at some point it seems to come to this minimum and then eventually comes back up. And then, like I said, once x is greater than 1, well, we know it's just going to keep getting bigger and bigger. So that's a really good question about the way it behaves between 0 and 1, how it actually comes down. Okay. Is there not something? Yeah, sorry, go ahead.
Tony, so is that like way because it goes through 0, 1 based on like the power because it goes to 0 and 0 and it passing through 1, 1? Is that what differentiates it from being an exponential function because it's the same exponent?
Well, what
same
differentiates it is the fact that the base is also changing.
Yeah,
in an
it's the same thing.
exponential function, it's a fixed base. So that is the big distinction here. In the same way that what distinguishes it from a polynomial is that in a polynomial, the exponent is fixed, whereas here. So this is why it's a completely different function from both an exponential function or a polynomial function. Okay. So what about here? Is there something happening with the derivative? Because remember, I'm trying to draw the derivative here. Is there anything interesting going on between 0 and 1? Yeah, Anna.
There seems to be like a point where the slope is 0.
Yeah, it looks as though somewhere here, I don't know, maybe at about 0.4, 0.38, there seems to be a point where the tangent is exactly horizontal. So presumably I would expect the derivative to be 0 somewhere around here. Then what's happening to the slopes of the tangents as I move to the right? Who can tell me what's going on with those tangents? Yeah, getting bigger and bigger and bigger and bigger. And what's happening as we go to the left? Well, they're becoming negative. But let's take a look. Clearly, as I move to the left, the slopes are becoming negative and they're becoming steeper. But what's the question we have to ask ourselves as we're getting closer and closer to 0? Anybody have any ideas as to what I might want to consider might be happening? So clearly they're getting more and more negative. But if you look really, really close, do they keep getting more and more negative? Do they seem to be yeah, go ahead.
Could it be an asymptote to going towards negative infinity?
Well, does it not look like it's starting to approach an almost vertical line, the tangent?
Yeah, because it goes into negative and then it just continues going steeper.
Yeah, so that would be interesting to see. Does it sort of approach a fixed number or does it continually keep getting more and more negative? So this is where we'll let Desmos do the work for us and see what happens. So, hey, we have our, I guess I was a little off. It looks like that, that horizontal tangent seems to happen a little further to the right. But as we said, hey, it's going to positive infinity. And if we take a look at the slopes of the tangents as we move to the left towards 0, yeah, they do seem to be approaching negative infinity. So it seems to be approaching this, vertical tangent, which of course, what is the slope? What do we say is the slope of a vertical tangent? How do we describe the slope of a vertical line?
Wouldn't it just be undefined?
Exactly. We say it's undefined because, it's getting either so big and positive or so small and negative that it just keeps getting, smaller and smaller and smaller. Okay. So it's interesting because in the end, in terms of the function itself, it seems to be a relatively simple function in the end. Okay. So let's now go back, and while I switch over, what I want you to do is I want you to, so we've answered A and B there from that question. I want you to go to C, and I want you to think about what the limit definition would do with this function. So use the limit definition of the derivative and see if there's any algebra you can do. Okay, so I'm going to switch over, and while I'm doing that, see if you can figure out anything you could possibly do with the limit definition of the derivative. Okay, so any ideas? So if you recall, when we were doing the derivative of x to the n, we sort of found a way to look for a pattern to expand this power here. And then we were able to do some work and figure out what the derivative was. And when we were working with an exponential function, remember the base was fixed, and we were able to use our exponent rules. Okay, could you use the exponent rule on this here? Well, let's see. I have a power, I have a base,
Yeah.
and there's a, so for sure I can do the same thing. So let's see what happens. Okay, so this would be, I guess, x plus h to the x times x plus h to the h minus x to the x. And what is the nice thing that is not happening here that did happen when we were trying to find the derivative of an exponential function? There's something that we're not able to do in this scenario that we were able to do when we were determining the derivative of a to the x. So if you remember that, yeah.
We're not able to factor out a constant.
Yeah, we're not able. So when we had a to the x times a to the h minus a to the x all over h, remember we were able to factor out this a to the x. Okay. And like I said, when we were doing the derivative of x to the n, we were able to expand that binomial. And the issue here is that we can do neither of these things. So the limit definition is really not of much use to us here. Like we can't even reduce it like we did with exponential functions to like a nice limit that we could investigate. There's really nothing we can do here. All right. So this is where we have to take a completely different approach to solving this problem. Okay. Now, what's nice about it is it's actually going to open up the doors to solve a whole bunch of problems that involve any combination of a variable in the base and a variable in the exponent. So not just x to the x, it could be sine x to the ln x. Okay. And what's nice about this method, like I said, is it's going to apply to all of these scenarios. Okay. So what I want you to think about is I've got this function y equals x to the x. And I would like you to go back and think about all the tools that we have. Okay. And this issue that there's this variable in both the base and the exponent. Can you think of a tool that we have at our disposal that would help us write this in a way that might take away the problem that we face of not being able to deal with a variable in both the base and the exponent? So think about what you might do. Okay. I'll give you a couple of seconds to think about that and maybe give you a hint if needed.
Well, I don't know. Would you use logarithms?
Well,
Or not?
what is it and why logarithms? What is it that logarithms allow us to do that has been very useful for us in the past?
Understand exponents, kind of like.
Yeah.
I don't know.
Yeah, oh, no, stay on the exponents thing. So Sammy, maybe I think Hannah had a good idea. So help me out here. What particular thing do logarithms do?
I'm thinking like logarithms let you, using like the ski slope, bring down that exponent into the like main part of the function. So it becomes like a multiplying it.
There you go. And we've kind of said that. We've done that in the past in advanced functions, where you said, well, hey, I have this thing in the exponent and I don't really want it in the exponent. So, hey, let me just get it out of the exponent. But of course, we have to do that legally. Okay. And what's one way of doing that is to take the logarithm of both sides. Now, what logarithm do you think I'm going to use here? I clearly can't use log base x because, again, like exponential functions, logarithms have to have a fixed base. So what logarithm, if you had to, pick one, especially since we're eventually going to be looking to take a derivative. So I think I saw Zavarier's hand. Yeah. What's your suggestion?
So would we have to use a natural logarithm in this case?
I think that makes sense. Okay. Because at some point, remember what our goal is. Our goal is to find the derivative. So if we're going to be using derivatives and involves logarithms, it makes sense to take the natural logarithm of both sides. Okay. And of course, why is this of use to me? Well, because of what I can now do on the right-hand side is I can now use that good old ski slope rule and rewrite the right-hand side in terms of a product instead of an exponent. Okay. And now all of a sudden, do I have something I can take the derivative of? Yeah.
Yes.
In fact, yeah, we've taken this derivative, I think, at least a couple of times now. All right. But I guess if I'm going to I can't just take the derivative of the side, and I'm not even sure what that would give me. But in the end, remember what I'm trying to find is the derivative of x to the x, which is what I've called this y. Okay. So does it make sense that I should just try to take the derivative of both sides of this equation? Okay, let's give that a try. And if you think about it, we've kind of done something a little similar when we were determining the derivative of logarithms themselves. Okay, is we rewrote a function in a way that involved exponents. Okay, and we use the fact that we knew those derivatives. Here I know how to take the derivative of xl and x. So let's see what happens when I take the derivative of both sides. So is there any issue with the right-hand side? So I think we can agree this we know how to find the derivative of, no problem at all. What is the issue though with the left-hand side? And again, this is a problem we came across a few days ago. What is the problem in taking the derivative of that left-hand side?
It's not in terms of x.
Exactly.
X thing.
I'm taking a derivative with respect to x, but what I'm taking the derivative of is ln of y, okay? But what I want you to remember is that y is itself a function of x. So essentially, what am I going to have to use in order to take this derivative, okay, of ln of this function, which itself is a function of x?
Chain rule?
Exactly. We're going to have to use the good old chain rule. Okay. Because this, even though it might not look it, if you take a look really quickly, this essentially is a composite function where the inside function is my y, which is x to the x. And then I'm taking that output and sticking it into the natural logarithmic function. So it's a composite function. And what does the, chain rule say I have to do? I have to first take the derivative of the outside function. So think of this as ln u. What is the derivative of ln u? Well, it's just 1 over u. Okay. And then I have to multiply that by the derivative of, oops, I was thinking ahead. I have to take the derivative of this inside function with respect to x. Okay. Now, we're going to do this part really quickly, but I want you to think about what this is going to start to look like. Okay. Because remember, I'm going to want to keep everything with respect to x. So let's do this right-hand side. That's pretty easy. Derivative of the first is just 1 times the second, ln x, plus the first function times the derivative of the second, which is 1 over x. Nice and easy. But of course, what does y represent? Y is just equal to x to the x. So what do we have here? 1 over x to the x. And lo and behold, what pops out in doing this process? Exactly the derivative we're looking for. Is this not the derivative we're looking for? There you go. Okay, so if you think back to how we determined the derivative of logarithmic functions, I'm hoping you're going to see a very similar pattern here. Because now, what's the last thing that needs to be done here? If this is the exact object I'm looking for.
We have to isolate it.
There you go. You just isolate it. So what we're seeing here is an indirect way of finding a derivative. Is instead of finding the derivative of x to the x, we find the derivative of ln x to the x. And in that process, what pops up? Exactly the derivative we're looking for. So what is the derivative of x to the x? It's just x to the x times ln x plus 1. And there we go. That's it. That's the derivative. Okay. Now, because this is an indirect method for finding a derivative, and it involves taking a logarithm to find this derivative, well, I don't think you're going to be too shocked as to what this is called. Anybody want to hazard a guess what we call this method of differentiation that involves taking logarithms?
Logarithmic differentiation.
There you go. This is an example of logarithmic differentiation. Okay, where you, instead of working with the original function, you work with the logarithm of that original function, which allows you, in this case here, to use the logarithm rules to rewrite the expression in a nicer way. Okay. And then in that process, you're able to find the derivative of that exact function you're looking for. Okay. Now I'm going to focus here on using logarithmic differentiation for these types of functions where we have both the base and the exponent having a variable. Okay, but just to give you a sense, I think there might be an example, of worked out example in the textbook. Okay, but I'll just give you a bit of a flavor as to how else this idea of logarithmic differentiation can be used. Okay, and I'm going to make up some real ugly functions. So I'm going to say e to the 2x times x cubed plus 7x to the 5, which actually you should know is not that bad on its own, but now I'm going to make it much worse because I'm going to divide this by x squared minus 1 to the 4 times, I don't know, sine squared x. Okay. Can you find the derivative of this function?
With a lot of algebra, maybe.
Yeah. Oh, you certainly could find 100%. This is a totally doable derivative. Okay. Can we see that you'd have to use the quotient rule? Okay. And can you see that you would have to, in determining the derivative of the numerator, you'd have to use the product rule, but then you'd also have to use the product rule determining the derivative of the denominator, and you'd have to use a whole bunch of chain rules in there. So it's certainly doable, but this would be, this would take you this might take you 10, 15 minutes to just get through this one derivative, doing it carefully so you don't make a mistake. Can anybody see something I might do to both sides of this equation that would take this combination of multiplications and divisions and turn it into something a little more manageable? What takes multiplications and divisions and makes them more manageable? I'll give you a hint. We just saw it a few minutes ago. Come on, what takes multiplications and makes them easier? What takes multiplications and turns them into additions?
Can't we use logarithms?
There you go. You would do the same thing as we did before. You take ln of both sides. I'm not going to write this whole thing out because it's too long. But now what could I do? I could use the logarithm rules to split this up as, well, the log of a quotient is the difference of the original logarithms. And then the logarithm of a product is just the sum of the individual logarithms. So you should be able to write this thing as ln of e to the 2x. Actually, that's really nice. Okay, plus ln of x cubed plus 7x to the 5th minus, I should put big brackets there, minus, and then this whole thing, but that's a product, and that would be ln of x squared minus 1 to the 4, and then plus ln of sine squared x. And can you see a whole bunch of nice things you can do here? See how these cancel out? What can I use here to make my life simpler?
Like ski sloping it?
Ski slope rule, ski slope rule, ski slope rule. Okay. These individually are all relatively easy derivatives to take, especially after applying the ski slope rule. And it's just a bunch of additions and subtractions. You don't have to deal with that mess that is the product rule and the quotient rule. And when you take the derivative of that side, much easier. And the derivative of this side is exactly what we did before. What's the derivative of ln y? Well, it's 1 over y times the derivative of, y with respect to x, which is exactly that thing we're looking for. Okay. So this method of logarithmic differentiation can sometimes be used on derivatives that you actually can find with more traditional methods, but making your life much easier because, again, taking derivatives of sums and differences is much easier than taking derivatives with a combination of products and divisions. Okay, so if you did, in the textbook, want to practice one of these or look at the example that's done, hey, go ahead and do that. All right. But like I said, for this lesson here, we're going to focus on the types of functions where we don't have alternatives. Okay. And before we do that, let's just take a quick look. Let's go back to look at Desmos there. Okay. And I'm going to type in, I'm going to make sure that I didn't pull the wool over your eyes. So let's take a quick look here at Desmos. Okay. So here we have the blue function, which is the derivative. Let's now put in that function we just found. Equals, and that was x to the x. And let's multiply that by ln x plus, and let's see, is it going to be the exact same function? And lo and behold, it is that function. So we were certainly correct, I guess you can't really see the difference. There you go. You can see they're the exact same function. All right, just in case you had any doubts, what we did is working. All right, so what I want you to do now is I want you to try on your own to determine the derivative of this function here using the one we just did as a template. Okay. Like I said, the ones we're focusing in on here are the ones where the base and the exponent both contain variables. Okay, I want you to apply the exact same principle we just used to 2a. So I'm going to pause. I'm going to give you some time to work on it, and then we'll take it up. Recording again. All right, so let's take a look at this one here. And what we're going to notice is that it's essentially the exact same algorithm as before. So step one, who's going to tell me what the first step is?
You take the ln of both sides.
There you go. Okay. So anytime you see variable in both the exponent and the base, essentially that's going to be your first step. Okay. And as you get more proficient at this, I would probably skip this. I would probably go directly to where I've used, which now becomes the second step. What is the second step here?
Use
And it's-
ski slope rule.
There you go, is you're going to bring this down, ski slope rule. So ln x times ln x. Okay. Now I could, when taking the derivative, I certainly could use the product rule here, but who's going to tell me what I'm actually going to use instead?
You could do ln x and then all that squared.
Yeah, that makes a lot more sense. Okay. So here, this is just ln x squared. Okay, perfect. Next step. What's the next part of the algorithm? So now I've taken log both sides. I've applied the ski slope rule. I also did a little bit of simplifying. What is the next step in the algorithm? Can somebody else give me that? Maybe even somebody who hasn't chimed in yet. Yeah, Zavarian.
I'm just thinking for the left-hand side, can you alternatively written as, I guess, 1 over y, and then for the right-hand side, write it as like 1 over x whole squared, then work from there? Or is it just going to overcomplicate things?
Well, no, I can't just write it. Oh, you mean like actually flip it around? Like take the reciprocal of both sides?
Yeah. So like breaking it down into like the equations for like ln y or like.
That feels
never
like
mind, actually,
overcoming.
it's
Yeah,
wrong.
that feels more complicated. So what should I be doing at this point? Again, follow the previous one that we did. What would be the next step in the algorithm?
Take the derivative of both
I think
sides.
now we're ready to take the derivative of both sides. Okay. So again, I'm kind of writing out all the steps really explicitly here. Okay. Always good when you're doing these things for the first time. And now again, same thing as before. We have to apply the chain rule here. So first I have to take the derivative of the exterior function. So my natural logarithm, what's the derivative of ln u? 1 over u times the derivative of that inside function with respect to x. And then here we can, as we said, use the chain rule instead of using the product rule on that there. So again, derivative of u squared is 2u, so 2 ln x, okay, times the derivative of ln x, which is of course just 1 over x. And now we realize this is just the derivative of that function we were looking for to start off. And then here we'll multiply the y to the other side, but of course, what is y equal to? Just x to the ln x. And then here we're just left with 2 ln x. And I guess we can put the whole thing over x. Okay. Now I'm imagining you can see that we could probably come up with a formula when we're working with logarithmic differentiation, because what always shows up as part of the derivative of this function with an exponent in both the base, power function with a variable in both the base and the exponent, what always seems to be showing up?
That original function.
That original function. So in that sense, you can see a similarity to exponential functions and their derivatives, but of course, with more complexity. All right, so let's give you a bit of time to work on this last one here, but I think you're going to see that there really is a pattern, and in some ways, that's what we like, is we like this work, this investigation, ideally to lead to something that's algorithmic that we can just do without having to think about too much every time. Okay, so I'll give you a couple of minutes to finish that one off, and then we'll take it up. And I think that'll be it. Okay, so let's take a look at this one here. And I'm going to do this one a little quicker here. So here, what I would do is I take ln y, and I know I'm taking the natural logarithm of the other side. I'm going to apply the ski slope rule right off the bat. That's equal to cos x ln of sine x. Okay, so this is where you start to save yourself some time. In the next line, I'm going to take the derivative of both sides, but I'm going to apply it right away. I'm not going to write out d dx of ln y. I understand that I'm taking the derivative with respect to x to both sides. So I know this is just going to be 1 over y times dy dx. Okay. And this here, now I'm going to have to do the work. So this is going to be, well, derivative of the first, negative sine x times the second function, and then plus the first function times the derivative of the second function. Now this is where I have to be careful when I'm taking the derivative of ln of sine x. What am I going to have to use when taking the derivative of ln sine x?
The chain rule.
Yeah, I'm going to have to use the chain rule. So here, derivative of ln u is 1 over u. So it's times 1 over sine x times the derivative of sine x, which is cos x. Okay. So here now, this is the derivative I'm looking for, the derivative of y, which is derivative of sine x to the cos x. Okay, that thing I was looking for. And now I know I'm going to have, you know, sine x to the cos x, because I'm taking this y and multiplying it to the other side. And now let's try to simplify this here. So I'll put the subtraction one on the second side. I'll just flip these around. It's always nice to start off with the positive one. So here, what do we have? We have cos squared x over sine x. And then here we have minus sine x ln of sine x. Okay. And could we simplify this a little further? You know, sure. You know, if you wanted to, you could write cos over sine as cotangent, so you don't have that. So you don't have that denominator. But I'm just going to leave it at that. At this point here, I don't think it's worth the time to simplify that any further. All right. So any last minute questions on this method here? Okay. So if you, like I said, obviously this is not part of, you know, in the past, I would have done this as part of the course's curriculum. It was a bit of a bonus thing. So obviously you don't have to do these questions. What I'm going to suggest as things you might do is I'm just going to give you a few from page 582. So there's number 2D and 6. And the reason why I'm just suggesting these is because there's already videos on those. And I think I'm going to see if I put them, I'll attach them to the playlist. Okay. And if you want to practice, sorry, this was 2D. If you want to practice, you know, using, we'll call it logarithmic differentiation as an alternative to product or quotient rule. Okay, so similar to the example I showed you on the last page, I would say number 9 and 10 are two nice ones where it actually, I would say, is worth using logarithmic differentiation. Okay, so it's essentially the exact same process as what we saw in these examples, except instead of making use of the ski slope rule, you're making use of the product rule and quotient rule for logarithms instead of the ski slope rule. Okay, but it's the same idea, is that you're taking a more complex expression and using logarithmic properties to turn it into an easier one. So here we know that multiplication is easier than exponents. We know that addition is easier than a product. Okay, so are there any last minute questions? No, so thanks for coming. We got in right under the hour. If you do work on any of these and you want me to take a look at them, please don't hesitate to come and see me.